Hello, in this video we are going to do a simulation on the Arduino UNO microcontroller. So we will use Proteus Design Suite, which is a software simulation that can be able to help us to simulate microcontroller and other advanced electronics. So firstly, you go to new project. You can click on the new project, so it will ask you to enter the project name. We are going to name our project for, let's say, LED. So this is our project name, and the path is where you will save this project. So I will click on browse. Maybe we go to 2025 project. So we save this in this folder. So you can click on next, and the next widget is about the schematic design. And in this widget you can simply click next. And for the firmware we don't need, so we can click next. And for the schematic, yes, we have the schematic. So this is our window. So in this window you are going to see the tools that are required for you to perform simulation on this workbench. So we can now select the component for the project. So under component we can click on the pick device, and we can start by typing Arduino UNO. So it will automatically gives us the Arduino UNO that we need for our project. So I can click this one, double click to save it in the workspace, and we can say LED red. So we want one LED red, so we can check. So we select this LED red, let's say LED green. So this is our LED green. We double click to select, and LED yellow. So we have the LED yellow, and we can have LED blue. So this should be our LED that will be used for the simulation. And we can just select the resistor. So we double click on the resistor, and I think we are done. So in our window we can select the Arduino component. We can place our Arduino, and we can see this Arduino have analog pins and it has a digital pins. So analog pins normally accept analog signal, and digital pin normally act as an input and the output to the microchip. And we have the pin number that are assigned to each of them. So we can start our connection. Since we have 4 LED, so we should have the limiting resistor, and we can change the value by double click on the component. Let's say 220 ohms. So we normally write 220R. So we do the same for all the other resistor, and we have 220R and 220R. So we can connect the LED. So if you want to rotate the component, you can press the space key by default on your computer, so it will rotate the component for you. So we have blue, we have the green, and we have the red, and we have the yellow. So maybe we can space them out equally. So to drag the component, you can just click the component and then you drag. So now I think all our components are in order. So we can just put the resistor in order, and this one in order. So this is like an open circuit. So we connect to pin 0, this one to pin 1, this one to pin 2, and finally this one to pin 3. So this is an open circuit. To make it closed circuit, we normally had, if you come to the terminal, where you will find some input, output, power, ground, and so on. So we will select the ground to make the circuit complete. So we can select only one ground and connect all the output of the LED. So this is now our circuit diagram for the 4 LED. So we have yellow, blue, green, and red. So we want to program them in such a way that they will have to blink. So there are many different ways in which you can make the LED blink, from simplest to some of the complex program algorithm that you need. So in our simulation here, we will use the Arduino IDE, which is the software that normally helps us to convert the high-level programming language to a low-level programming language that can be used by the microchip. And since it is mostly binary, the file will be in hexadecimal, and the microchip will decode into binary, which can feed those LED. And now I have opened up a new sketch for the Arduino IDE. So this is the software that normally used to program the Arduino. So firstly, we can save this project into our folder, because it is very important to save into a specific folder. So from there you can be able to retrieve the code once it is compiled. So I can select new folder, let's say the code, and inside this folder we can say for LED. So we save the file. So it is important that you know the location where you save the file, because later on you will be able to redirect the microchip in Proteus to locate the hexadecimal file. So by default, this is the layout. You have the void setup and the void loop. So we will mostly put our code here. For the void setup is where we declare. We declare, for example, the number of pin. We declare if we are using some LEDs as an input, output, or if we are using LCD, or if we are using communication protocols such as GSM module or serial terminal. All of these we can declare them under void setup. And under void loop, it says it usually run repeatedly. So it is like a cycle. Whatever code you insert under void loop, it will continuously run. So it is basically these two which are very important. So let's see if we want to now include our pins. So we all know that our pins are connected to the microchip, and we can say integer. We now declare the pins as an integer, and integer normally takes a value. And if you are dealing with a floating point value, then you should declare it as a floating number. So for our LED, we declare them as an integer. So let's say LED pins. So those are our LED pins. So we will use a for loop to program the blinking of this LED. So we put a square bracket where it will have the values which will increment. So increment from a specific order from, for example, 0 to 1 to 2 to 3. And then these 3 pins represent the order in which the LED will blink. So from here, we can understand that our pins are 0, 1, 2, and 3. So these are our pin. And we normally put a semicolon at the end so that it will tell the compiler that this is the end of our code. So without this, the compiler won't be able to understand that this is the end of your statement. So all this line can be regarded as a statement. So after every statement, you have to put the semicolon. So under void setup, we can now be able to specify the algorithm in which these pins will be declared as an input or the output. So we can use the for loop. So let's say for the integer, which is I, is equals to 0, then the I must be less than 4, and we have I plus plus. So that means the I will start having a value of 0. That means for the LED pin. So it is like a countdown. So it will count from 0, the next, the pin will move to the next, which is pin 1, pin 2, pin 3, and pin 4. So in that case, it will blink the LED. So after the for loop, we now have a bracket, and we now specify the pin mode, which is the LED pins, and we have the I, which will increment, and it is now the output. So in this statement, we now telling the compiler that this is the incrementation of the signal, and those LED pins, which is connected to pin 0, 1, 2, 3, and 4, all of them are the output pins. That means this pin is made as an output, and it cannot accept any signal coming in, because those are digital pins that act both as an input and output. So in this section, we have this statement telling the compiler that all those pins must be the output pins. So once we are done with this void setup, we now go into the loop. So in this loop, we now will have to tell the compiler to perform the indentation. So we normally use for open and close bracket. So integer I is equals to 0, and I is less than 4, and we have I plus plus. So I will explain later what this really does. So to write the pins, we have the digital write, which is a command that will tell the compiler to write the digital signal. And in some of our video, we said that a digital signal is having two binary states, 0 and 1. When it is 1, it will give us output of 5 volts. And when it is in a low state, it will give the output of 0 volts. So we can say digital write, and we have our LED pins having the integer I and high, and we give a delay of, let's say, 1000 milliseconds, which is equivalent to 1 second. And finally, we can say digital write, and we have the LED pins I, comma, and low. So this is another statement. So this is our code. So I will explain. So in the first, we are now declaring the pins. That means if you have to write a comment. So to start a comment, we have double slash. So double slash is a comment, and it tells the compiler that anything after the double slash is a comment and cannot be executed. So in this first section, we can say assign the pins for the LEDs. So we have done that. We assign one pin to pin 0 and the other one to pin 1, pin 2, and pin 3 of the Arduino microchip. So in this section, we are now declaring the pin as an output pin. So we are telling the compiler that all those pins must behave as an output pins. So in this case here, so we have the for loop which perform incrementation. That means it will count for the first loop. Since it is going in a loop, it will check if I is equals to 0. That means for the first loop. This normally performs the incrementation. So in the first round for the loop, it will check integer, the first integer I is equals to 0, then it will execute the pin 0, which is the first pin. It will be high, that means it will be on, and after 1 second's delay, it will register low, that means the LED will go low, while all the other pins will be low. So when I is equals to 0, and then this condition state that 0 is less than 4, it is true. So I plus plus, that means it will increment 0 plus 1. So the I will have the value of 1. So in the next case, I is equals to 1. Then when I, which is 1, is less than 4, it is true. And we have I plus plus, which is 1 plus 1 again. So it will execute this when I is equals to 1. And when it is incremented, it means I is equals to 2. So when I is equals to 2, that means 2 is less than 4. Then this is true. So now 2 plus 1 is equals to 3. After executing this code, I is equals to 3. So 3 is less than 4, true. Then I plus plus 3 plus 1 is equals to 4. So after the fourth LED blinks, now we have I is equals to 4. So when I is equals to 4, it will check. 4 is less than 4, it is false. So after this, to check our code, we normally click this tick button, which is compiled. So if we want to check whether our code has errors or not, we normally click this one. So you will have this window popping up. When there is no error, it will say done compiling. So since we are not using the Arduino, we are using a virtual Arduino. So this virtual Arduino will require a binary format to execute the instruction. So we normally go to sketch, and we are now going to export the compiled binary. So we have performed compilation of this code, and now we are going to export. So you will see it is done compiling. That means it is already exporting this file. So as I make mention, you have to know where you save this file. So we are going to check whether this binary data is saved, so we can use with our Arduino. So you can go to your folder where you save the Arduino file. So this is where I save my Arduino file. So you will see a new folder is created and it says build. So you will just click on this build, and once you are in the final folder, you will see those are the exported file. the only file that we need for our Arduino project is the .x extension, meaning the type it is a hexadecimal file. So this hexadecimal file contains all the binary information that is needed for the LED circuit, and the microcontroller will mostly use this file. So since we know this file, now we will go to our Pro Tools to import this hexadecimal file. So now we are back in our Pro Tools design. So we can now double click on this Arduino. So in here, you will see it says program file. So we will go to our hexadecimal file I have shown you earlier. So we click this one and we go to code for LED build Arduino, and now you have this hexadecimal file here. So you just click and open and then click OK. So now the file is already stored in your microcontroller. So you are now ready to program this blinking of the LED. So you will come down here, you see the play button. You will simply click this play button to simulate the microcontroller and the LED blink. So now you can be able to see that those LED are blinking with a delay of 1 second. So this is how we program the Arduino microcontroller to perform operations such as blinking the LED. And there are more other applications that we will look later on with respect to Arduino and other microcontrollers such as the big microcontroller, STM microcontroller, ESP microcontroller, and so on. So this is a simple explanation that deals with the blinking of the LED with respect to 1 second. So if we want to delay the blink, so for example, if we want the delay to be 2 seconds, now let's see how we can do this. So we can simply modify the code without actually rewiring the circuit. So that's the beauty of a microcontroller. So we will go back to our Arduino IDE, and in our microcontroller IDE, we now see this delay. So this delay is responsible for the time delay between the transition of the eye, which we say 10 LED on and 10 LED off. So this delay in between specify the transition between the on and the off. So if we now increase to 2, that means 2000 milliseconds. So it is equivalent to 2 seconds. So all we have to do is to verify, in which we compile the sketch, and then we go to export compile binary. So after that, it is already exported and it is saved. So we can now go back to the Pro Tools to see what will happen. So we can come here. If you want to stop the simulation, you can click the square button and you have the pause, which if you want to pause the simulation, it will pause. And if you want to play again, you can click the play button, it will simulate. And if you want to stop, you click this one. So you can double click again, you come to this Arduino, select the X file and click OK. So now we know that there will be a delay of 2 seconds between the transition between high and low between each of these LED. So after 2 seconds, it will go low and the other one will blink. So this is how we normally specify the time delay between the turning on of each of these LED. So example, if we want to make it go a little bit faster, that means we simply decrease the delay time. So let's see how this is done. So in our program code, we can now say, let's give 500 milliseconds. That means half a second delay. So we can just compile, and we go to sketch and export compile binary. So after this, we can go back to Proteus. So we are now in our Proteus. We can just select this one and click OK. And now we can start simulate. So now it is running on half a second's delay. So you can see that this LED is blinking a bit faster than 1 second and 2 seconds. So this is how you program the LED blink between 4 light emitting diodes. So in our next video, we are going to look at how we can perform blinking, and also by adding some push button to select which of the LED can blink depending on the push button. And also I will also introduce to some of the easiest way in which you can apply blinking without the for loop